So my name is Dąbrowski, and I will be talking here about simulation and trucks. So it's not cars like the usual in this method, trucks. The presentation will start with just a brief introduction and a rationale for why to simulate. Many of you probably understand this very well, but I will go over it again. And there is a section about overview of simulation tools, mostly open source tools. And in this section, simulation tooling, I will be very interested about your feedback. So your experiences with simulators. I know probably among you there are some very interesting experiences. And then there will be two case studies from the projects that we did in Robocar. One will be concerned with the mine operation, the tracks in the underground environment, and the other is the harbor. And in the end, of course, there will be time for some questions. So that's the team. I'm a graduate of computer science / IT department at the University of Warsaw, and I used to work in like 5 years in software engineering in general in various kinds of companies, and then I moved to robotics, and I'm very happy about it. It was like 5 years ago, and I think it was a good career choice. And here is the entire team which was involved in the projects that I will talk about. Our company is a bit larger, but not too large yet. We are expanding, and more about it on the last slide. So, of course, like the name of the company suggests, you could probably figure it out. We do robotics and also some machine learning. Okay, so why to simulate? Of course, all major players simulate. You have some kind of simulation solution because simulating and crushing a virtual car is much cheaper than crushing a real one, but also for a variety of reasons, like you can generate rare scenarios, which are very difficult or dangerous to recreate in reality. For machine learning, you can generate tons of data from simulation. And of course, it's very easy to move to a different location, test different maps, test different sensor layouts. So all in all, it's a must when you're developing solutions for self-driving cars. And of course, here we'll focus on some prototyping of algorithms and also on the scene generation. And our use cases are concerned with real vehicles, so not just simulation, not just for the purpose of testing an algorithm, but as a way in a pipeline, as a point in a pipeline where we in the end deploy the solution and drive on a real track, which is for most self-driving cars or whatever still science fiction. So about the tooling, the simulation tools. You know Carla probably around here. All right, who knows Carla here? Maybe raise your hands. Okay, so not that many people. Just to probe the background, who is a software engineer of some kind? Come on. All right, that's better. So it's about the profile of the talk, how technical I can get. So you can see two screens here. The left one is Carla, the right one is AirSim. Actually, both are Unreal screens because that's the engine, the visualization, the physics engine, the scene engine. So Carla main use case is testing machine learning solutions. So it's for autonomous driving perception. It's not the same use case as we've had, right? They're important changes. Carla is an interesting project, I think the most interesting. It's still developing. I think the last version was 0.91 or something like that. And it's very promising, of course, we are observing it, and I will be very curious to hear the talk about this later today. So, Carla comes with a scene in Unreal, which is a part of a small town. There are some cars, there's a town, there are some scenarios where you can drive the cars around and test some very basic things right now. AirSim is another open source tool from Microsoft. Air in the name is from the fact that it also serves to simulate UAVs, so drones. So it's a kind of dual purpose there. The scene that they provide with the project is very basic, as you can see in the picture. The advantage is that it builds without any problem. Like I had problems with building Kala. I needed to use my software engineering skills instead of just following the instruction. More simulation tools, open source. There is Gazebo. Who knows Gazebo? All right. So it's an open source robotic foundation tool which has legacy already. It's quite mature. The version is 9 point something right now. The primary use case is from the world of robotics. So robots can be Roomba-like or humanoid-like. This is a bit different than automotive. So its primary use case is to simulate populations of robots. But also on the screen you can see there's our entire world and a model of the car coming from NVIDIA Challenge, which it's a previous model. It was a challenge for machine learning applications for self-driving cars. Another tool is, Apollo is a project which emerged recently, but is huge because I think it's Chinese mostly, so there's a lot of traffic there. And the purpose is a bit different. This is like an entire framework to deploy on a car. You get a car with a certain set of sensors, and it's ready to go. I didn't test this because it's kind of you have to buy a car with the sensors, which is quite expensive. It's not a use case, but they also have a simulation tool which is called DreamSpeed. I don't think it's very sophisticated right now. It's a bit of a different use case. So, of course, that's not exhaustive list, but these are in some ways interesting ones. And if you know any other interesting ones that can be applied to automotive, then I would like to know. We can talk, or you can tell me now. Anyway, none of this just solves your problem. You have a problem. You want to simulate some kind of scene, a map, a vehicle, some kind of behavior. So you can't just take the tool and you're done. You have to develop a simulation scene. You have to put the correct vehicle model. Of course, there is the entire issue of developing the correct algorithm to drive it. And you want to develop scenarios as well, which are interesting for you. So also taking a tool that is already huge and is not exactly for your use case, it's a bug. It's something you need to support. Sometimes it's better to have something like it. So one tool that is the framework, a middleware, which is very useful in robotics in general, is ROS, the robot operating system. There's a reason why that every simulation tool I mentioned has some kind of ROS integration. Gazebo, of course, has a very strong ROS integration because ROS is also from Open Source Robotic Foundation. This is the same entity. But every other also has some kind of ROS integration. So there are common things you want to do when you're developing a system, such as a system called self-driving and a simulation framework for that. Which is you need this entirety of communication, the plumbing, the tools for debug, for monitoring, for starting subroutines, programs. All this kind of so-called plumbing you can see on this bottom picture from the ROS page. This is what it provides. So this is publish, subscribe communication, and it's very convenient for extendable architecture where some entities are dynamic, so they appear, right? So of course it contains many packages. We saw various robotics problems like navigation problems, perception problems, so you can just use the code. And the community is great. When you build a project in ROS, you build it in a modular way, which is advised. It's is just very supportive of this kind of architecture. And it's becoming increasingly popular in automotive. I don't have stats, but we all get job offers quite a lot, and it's increasingly present in the office. So there is an entire field of discussion about this, about the industrial readiness of the middleware, but for fast prototyping there is nothing better. So everybody should use it. So there is also a second version. I advise you to check it out. It's already the third release of this version, so it's ready to be used. And it has also the greatest conference, I think, the community. It's called ROSCON. I very much like it. And on the last conference, like the focus moves towards ROS2. It's very visible, so it's something to consider. Anyway, if you like good colors and turtles, ROS is for you. As you can see, the logos are always, and the names of the releases are always some kind of turtle theme. All right, so as I mentioned, there is this task of creating a simulation scene. When you want to solve some kind of problem and simulate it, you want to be able to create a simulation scene in an easy way, have some tool for it. It's like with photo editing, you can use Microsoft Paint for photo editing, but you are much better off using GIMP or Photoshop, right? It's just there are tools for it that make it much easier. And our requirements were to create a network of roads pretty fast, and it's kilometers, like the degree of 5 kilometers. And precision, why precision? Precision with the geolocation, in the geolocation sense. I will explain later why it's important for use case. And also, of course, to have there is this wish in the entire community of simulation to have something that generates these kind of scenes in an automatic way from the recorded data. NVIDIA had some interesting results with GANs, with generative neural networks. But these are, I think, only in visual. We are here mostly using LIDARs. So you can see screens from a tool. We hired a professional company to help us, Vector Zero, and the tool is Roadrunner. So it can, we think it's really good. So we used it also ourselves. And I can see logos of some other software, some of you might know, which are very useful for generating scenes and meshes. So of course, the scene is not just the geometry and the textures, it's also logic of the driving, open drive data, so all the kind of meta information about the road. So you can know which side of the road the traffic goes, which direction. And still the roads are generated by some kind of simple curves, as shown there. And you can see there is elevation as well. Elevation, if you want to recreate a real place, right? So this is recreating a real place, not creating a fake town, right? Which is based on nothing. If you're recreating a real place, you need elevation data, of course. Unless it's very flat surface. So you can get this from some kind of organizations, government organizations. All right, so let's move to case studies. First case study is in the mine. So we have a track and it's in the mine. It's the limestone mine. First thing you can see, maybe the first thing is the track. But the second thing you can see in these pictures is like there is both open and confined areas. There is plenty of specifics to this, which it's different from the self-driving taxi in the urban environment, right? So we have low light conditions inside the mine, of course, GNSS, any kind of global navigation satellite system one vehicle inside this kind of line. So it biases towards choosing LIDARs. It's around 4 kilometers and it's intermittent outdoor, indoor, outdoor, indoor. And then the entire problem is to automate transportation of limestone. So there is in one place there is a bunch of mined limestone, like bricks. They are loaded on the truck, and they are transported to a place where they are crushed, and this crushed thing is taken away, right? So, so human drivers, you know, they just drive the same route all the time, right? They just drive this all day, right? It's kind of boring. It's a very good candidate for automation. The entire, you know, background for these use cases, why this kind of use cases, is that they are simpler, you know, it's a kind of low hanging fruits. So solving a problem of urban driving in a very complicated, unpredictable environment with other human beings, you know, it's difficult. This is simpler, so it's expected to hit the market right before. So we are solving this kind of use cases. All right. So of course there is this route. The source is actually, this is a public knowledge because this has been released as a PR video from Volvo Group. There is a source on YouTube. You can see the PR video. Everybody is happy about, you know, autonomization. There is good weather in a region where you can't find good weather, I think. So they chose a very specific day for that. But it's fun. It's a good video. We will share the slides later. You can just follow them up. Anyway, there are other trucks also because it's not just one truck going on this route. That wouldn't be very efficient. All right, so how to solve the problem? We were to start with prototyping. That was, by the way, it's not like we chose this order. It was how we got customer projects, right? They wanted us to do this in the first phase. You know, of course, we were advising a customer in this way. So we started with prototyping. What they wanted us to find, and what we wanted to find, were what kind of deep learning solutions can be interesting based on LIDAR data to find a path in this mine, not to hit walls, basically, right? So the background for this is that it was supposed to be also a primary system that finds the path, and this is a secondary system. Much like the concept of arguing machines. You know, there are two systems, each of them proposes a path to go. If they differ, the paths differ, then there is, let's say, dangerous situation. And in the transition phase, the human then takes over, and we find out what's wrong, and we fix the system. So they agree. You know. So we tested this approach as listed here. There are three. So first is neuroevolution of augmented topologies. So it's an interesting approach to neural networks, which right now Uber is heavily investing in. And how many of you are familiar with neural networks? Like, how much do I need to say? All right, that's good. I like that. No need for introduction then. So in normal neural network, standard neural networks, you have backpropagation as a mechanism to change the network from iteration to iteration. There is no backpropagation in neuroevolution. Instead, there are mutation. The topologies world, the word in this is about network topology, of course. So topology is also evolving, not just weights. So a new layer can be evolved as a mutation, added or removed, and the same in the layer, neuron can be added or removed. And of course, weights also change. So, of course, in this approach, there is something that needs to determine fitness. It's an evolutionary algorithm. So, of course, it's easy. It's similar to reinforcement learning. which has reward function. Not very easy to design in many cases, but the fitness is very much like it. So you can go like for a very simple fitness measure, which is how far you manage to go before crashing. So a distance travel. But of course you need to improve because you want to avoid some kind of wobbly behavior. You know, the track is kind of sniffing each wall. It's not very energy efficient, so you need to develop a little bit better the measure. You know. Anyway, the problem we started solving in the prototyping phase is quite easy. It's easy to train a neural network to solve it. We tried different approaches and learned how it goes. But not crashing into a wall on the map like you see on this in this Gazebo screen on the left side. It's not a hard problem. You don't need high LIDAR resolution. A problem of not crashing into the wall and keeping the distance, it's quite simple for neural networks. So there was reinforcement learning using the advantage actor creative. I won't be talking about it here. I will go into detail on imitation learning using convolutional networks. So imitation learning requires human data, right? So of course we had recordings of human drives. These poor truck drivers, who drive through the mine. They recorded some, they got sensors on the truck and they recorded some data on the drives. So we had the correct path to take by the truck. So the one that human, right? And we had LIDAR frames. So entirety. But of course, to approach it correctly, you need to augment the data because otherwise the system doesn't know how to behave once it's off the path, right? The human driver will always stay on the path, so you don't have this data which is, a bit closer to the wall. So it wouldn't be stable. So we augmented the data in a standard way as well by changing the pose of the track from recorded frame, like rotating it a little bit, changing position. And then this is on the screen, it's barely visible, I think. Yeah, so augmenting the data is quite easy. You change the position and you just do this transformation of the frame, of the LIDAR frame. It's of course not perfect. You can't go 5 meters ahead because you will see different things on LIDAR, but small augmentations like, let's say in a range of a meter or two, it's still good. And then it's easy to calculate a curve that comes back to the path. As a good thing that a human would do, right? It's an algorithm thing. So once you have this kind of data, you can train the solution for it. So I will have some movies here, starting with neural evolution. So it's a simple Gazebo track, but what's interesting is that the track wasn't didn't learn on this particular map. This is a new map. It hasn't seen it before. It's also much longer than the map you train on. It's a ninth generation from this neat algorithm, which took, I think, 6 or 7 minutes to run once we got things well configured and parameterized. And as you can see, it's not like a human driver unless it would be very bright machine, but it doesn't hit the wall, right? It solves the problem. Maybe not optimally, but it does. So yeah, it's almost the end. It's not sped up, the video. Oh, by the way, that's a monkey on a pillar. That's a monkey on a pillar. The Blender tool has this kind of standard monkey. If anybody, I see some of you nodding. So as a joke, we placed a monkey on a pillar. And also not as a joke, but to test, whether this kind of completely new thing could be, avoided. It happens. So what's interesting, the video is not sped up. We run the simulation with, there is a real-time factor around 4. The maximum we're able to have is like 20. It's also a matter of effective real-time factor because you can run simulation in parallel. Neural evolution is very good for parallelization because you have The one step is spawning a population of networks, let's say 100, and then you have to wait until all of them terminate to determine the most fit, right? The list from the top to bottom. So you have like 20 most fit reproduce. It's a cruel world. So the parallelization would be like you can run 10 instances. So 10 individuals in 10 different simulations can run at the same time, no problem, or 50. I think we run 7 because we have laptops, right? not some kind of. So you can run it fast if you get things right. It's a matter of getting physics right in Gazebo 2, and getting physics right when you are speeding up is not that trivial. You have to watch. So next thing is this CNN imitation. There is no simulation. Gazebo simulation is like a Python simulation or visualization. So we have two things happening here. You have the original algorithm was trained on the top one, the top map, but going in the opposite direction. So we wanted to test, the other direction, and the bottom one is the new map. So you can see the LIDAR frames, and in the next video it will be also important, so I will talk about it. So this slash on top is just the max range. It's not detection. Just max range is 1. Like you have to normalize the data from neural networks. So 1 is nothing in the range, basically. But it looks strange. You need to kind of see it. So yeah, it went through it, right? So it seems that the problem can be solved at least in several ways. Next one is also CNN imitation, but now what is not usual on CNN, we predict like the path. So it's 3 outputs, it's angles actually. So they create a path, right? 3 points ahead. Because if you want to go at a certain speed, you need some kind of, more prediction. So here we managed to train it on augmented frames from LIDAR data and based on a human drive. So what's next? Next, we are starting simulation now, and here.
What's the output of this neural network?
3 numbers. 3 numbers.
Speed, I guess?
No. There's no speed here. This is not yet the problem to solve. Besides, this is a part of the logic system. So it's a secondary pathfinding solution, which works in a complicated system where it doesn't know the speed. It must predict the correct path, okay? And the speed can be an input, but in this prototype version, it wasn't, right? Okay. So we assume some constraint on the angles, of course. So you can't just turn in place, right? Okay. Which would be matching for the speed that is typical, right? Okay. So how to automatically create a scene for this simulation? That's an interesting thing. And with LIDAR data, it's easier in a confined environment, because you get all that base, right? So we had this track with LIDARs. 2 of them were 3D LIDARs. One was kind of looking up and around, and the other one was looking forward. So we got this data, which is by no means perfect, because when you gather data for building reconstruction, you need to go slowly. The track was driving at normal speed. You don't have that good data then, right? Especially you have a track, the cabin moves. It's another difference with the cars. So if you're using SLAM algorithms, this is a factor to consider. The cabin has to move. So anyway, joining 2 or more sources of LIDAR data, joining them over time to create a large point cloud. But at the same time, remembering where was the viewpoint, because you need normals. Normals are the little white things that point to the inside or outside of the object. They need to be consistent. If they are not right, algorithms that recreate surfaces, they just fail. So we have this point cloud with normals in top left. Then there was some kind of first attempt with the algorithm. As you can see, it's not every algorithm, not every configuration gets it right. You have holes. It was still promising, right? We went further. This is a Poisson reconstruction with, I think, level 14, so pretty accurate. And what we found out that transformation we were using to join two different sources of LIDAR data is a bit wrong. So you couldn't see it in the point cloud because it looks like a point cloud and it's roughly good. But you can see this like there's something growing on the walls, right? So this is the only problem right now. The imperfection is easily fixable by aligning the LIDAR set with correct transformation, right? We learned that the one that we got from a customer is a bit off. It was okay for them, but for this purpose, with this kind of detail, there is some kind of funny effect, right? So this is quite good for automatic reconstruction. There is like no manual work in this. Zero, right? So of course, we need to handle outdoor as well. We need to join kind of pieces that you. It's still some work. This is just we are just starting, right? And we prepared some kind of video for the mining conference, so it's a bit like in a PR. Wait, this is the real video, the real track riding in the real mine in Norway, right? It's very cool. Yeah. It's up north. This is one of the LIDARs we use for field diffusion. As you see, there are ego detections that you need to filter out, so the car sees itself. And then there is a process, let's say, visualized to make it understood for business people as well. And it's increasing level of detail information. And of course, once you create this kind of mesh, you want some balance between detail level and the size of the thing, right? Then you can simulate a truck. Oh, there's sound. Oh, I hope you like engines. It's a Unity simulation, so we had this track put into it, and as you can see, that's something that was very well received. I was surprised we were able to do that in such a time. And of course, this is very preliminary. This isn't an effort of many hours of work. It's just it shows what can be done. I think it's a promise. The track is different, of course. Also, you can't load things on this term. That's an asset we have. So of course, there is LIDAR solution here. It's like conceptual. This is conceptual. Of course, you need to develop it further. But what's very good for a real use case is that you can see how the LIDAR from the simulation resembles the real one. And you can fix explanation. So now there is a concept of safety presented. Like there's a guy, the truck is going forward and he will stop. It's very unpredictable. I think it stops way too close. If it was a real human, he would run. I would run. But anyway, it shows the concept, right? So moving on, that's what we are doing now with the mine, right? So now we go back in time because this is a separate conceptual thing. So we start from the past here as well. This is a truck in a harbor. So the problem is we have a route in a harbor it's not a closed road, but there is not much traffic. You are not very concerned about there being a traffic jam, for example. What's important, there are intersections and roundabouts, and you have to obey the rules, of course. But the truck doesn't need to overtake vehicles, doesn't need to do any maneuvers. If there is some guy ahead of us and he's going slower than an autonomous truck, it's already a success, right? So in this case, if we have to wait for someone, it's not that bad, right? So we still need to detect all the traffic participants and react to them. If there's someone ahead, if there's someone on the intersection approaching, right, we need to yield. If there's someone on the roundabout, we need to yield. So even though the track stays on the path, it needs to understand what's happening to adjust the speed accordingly, right? So the problem was completely about the speed control of the track. The track should drive on a trajectory which is predetermined, you want to change, but it should stop, it should slow down, sorry, and it should accelerate back to the speed which is optimal once something is applied. So, it starts with perception. So our first task was to handle perception. And you can see real tracks are in play, right? We researched and chose the ideal solution. They have this setup with 5 LIDARs. ECU is for embedded computing unit. It's something that allows the software to integrate the LIDARs and detect objects. So it's good for detecting other vehicles, right? So we didn't want to implement this kind of thing. It's quite complex, right, to do it properly. They did it for like 10 years, I'm not sure. Like, it's a big team, 10 years. So it's better to use something that's already there. Anyway, the customer wanted us to have it interface to ROS. The project that we're using ROS, we were happy to use ROS as well. So once we prepared the software, we went with some IPO people and we deployed all the equipment on track. So you can see a bit of the setup. And there are 3 LIDARs in the front. 2 of them on each side are angled. And there are also LIDARs on the steps, which is a very, this is prototype. You don't want your LIDAR to be a bumper, right? But it's the first, let's say, the first iteration, right? So also in the target use case, there is a trailer here, but it's a bus carried around and turn around a bit. And of course, we need the trailer in the end to carry the goods, but right now we are testing this out. In the simulation, we already put the trailer because the simulation is good and it's much cheaper to do so. Anyway, we drove this track with this deploy setup. We added some utility and visualization tools, and we gathered the data. The second phase was actually to do something with the perception. Okay, we know there are objects somewhere of some kind, but now how to behave based on this knowledge, right? So it's a pipeline. It's a rule-based approach. It's not machine learning, right? It's a perception control pipeline. We found that in this case, where we have to only control speed, it's probably better. So what you can see here is some kind of logic for intersections where you have a car. It's a very preliminary, right? When you have a car in this area and it's going this direction, just here, right? The area activates, so to say, and it's something you need to stop, right? In here you can see the RVs, so our ROS visualization tool, which shows our illegal vehicle as a yellow brick because it's a very good representation. There is the white ones are LIDAR points, and there are red detections with classifications as well. So the detection comes with a classification of tag. It's a car, it's a truck, it's a pedestrian, it's a bike. It's sometimes wrong, but there is no false negative in detections, like we have. So if there is a vehicle in a distance, it's detected. There are false positives. So sometimes there is no vehicle, and we detect, let's say, something on the right side. Fortunately, false positives are all of this kind that they are not in the path ahead of us. they're on the side, right? So you can handle that. Yeah, so to make decisions based on that, we need some kind of logic for intersections, but we also need some logic for collisions and predictions of the movement based on this tracking from the system. And just also building an interface with the control system. So localization is not up to us. We get the localization from the system. We get the trajectory, and we output the same trajectory, but with a velocity profiler. So we have this speed suggestions for the system, right? So after that, let's say, should be a little bit before, but then the understanding of the issue grew, especially on the customer side. I think that simulation is very, very good here. You know, truck is even bigger than the car, and it's even more dangerous to crash it. So the task was to develop a simulation for the hardware, to prepare a simulation scene, prepare some architecture, acquire the track model, and connect the solution, the rule-based system with the simulation engine. And these are some strings from our simulations. We called it the simulation framework, and we used two engines for the simulation, Unity and Gazebo. So I think Gazebo is misrepresented here by this small screen. And you can see the Unity application running, and you can see the Airbus where you can see the car, this one being detected, right? And you can see that's a long stretch of road, it's just a fragment. So we prepared the entire simulation scene. And well, now there is enthusiasm to move further and use the simulation to validate the rule-based system, to improve it, and improve simulation, of course, because it's a process. And the goal is to drive through the entire region. How am I with the time, actually?
Yes. You have, let's say, 10 minutes.
I mean, okay, that won't be that long. Yeah. Because it's somewhere in questions, okay. So that's also actually like considerations are some, maybe the slide should be titled tips, right? So, simulation early as possible, you'll need it if you want to deploy the system, of course. There are some issues you need to think about when training, let's say, the evolutionary algorithm or any other kind, because if you have some issues with synchronization or large latency, and you're speeding the simulation up very much, and you're consuming a lot of resources, then the latency at one point during the simulated drive can be so high that the control system won't. You know, control system is perfect. The individual is good. He knows how to handle this map, right? But due to system latency, he will crash anyway, and he will be can't reproduce, right? So it's important to remember about that. Also, in the early Gazebo examples, we had this problem that then we have a resulting individual, and sometimes it couldn't drive. Like we have the recorded individual, the network, and it wasn't fully deterministic. There were cases where it didn't manage to get right. Of course, using your resources is important. I know there's cloud computing, you can pay for services, but also if you're designing your own simulation framework, think about parallelization and faster than time execution. Parallelization is very useful in always like, but for evolution, it's like I mentioned, it's very natural. It just improves what you have. For reinforcement learning, where you have subsequent rides and there is back propagation, and you have the result, you need to run one, but very fast, right? It's very good. Of course, you can parallelize with different starting configurations, but it's not the same, right? So also the aim, of course, the approach to the simulation is very different. If you just want to test your machine learning solutions, right? Then you can use Power, I guess, or whatever. But if you want to plan for deployment, then you need to think about verifying the simulation, because simulation validates the reality, but you also want the other way around. So you want to have entry points in your simulation for real devices, real data, real localization, right? So you can test whether your simulation is good. And ROS helps, right? So here's what can happen in the simulation. There's some, I spawned the truck. I think I spawned it here. Then it didn't start driving. It just slid down here. And, it's very, very much like it would happen in reality, right? And that's a case in Unity, when the trailer doesn't exactly attach to the tractor. So there are casualties, right? Anyway, it's fun playing the simulation of trucks. So now it's time for questions, and of course we are hiring. It's a fun job. We are expanding. We are successful. Come and join us. What are the questions? What is the feedback from the audience?
Okay, waiting for the first question. Anyone? Okay. Yeah.
How much difference you see between the real world and simulation?
Oh, we are not there yet. As you've seen in the...
But I heard you had experience in real world. So
Yes, but we are not yet on the phase where we have consistent real world driving, and we can see how... What's important here is which differences are crucial. It's understanding for a particular kind of algorithms that you have, for a particular use case, what do you need to simulate precisely, and what is just a waste of computing power. Like, you don't need like high texture birds flying over, It's a waste of resources. We didn't put textures on the buildings or shapes. Buildings are not important. We don't use buildings for anything. So of course, it's a process of planning, but we have plans on how to plug in the real data, both from the top. So we do the real drive, and we do the simulation, and on the top level we see what's the difference, and from the bottom, so from the sensors, right? We create geometry from the data, and then we simulate LIDARs on this geometry, and we see by some measures if point clouds are the same, right? So yeah, we thought about it, but it's not the phase where we implement it, right? But we will.
Okay, anyone?
Do you think using LIDAR is the future? Because now we are using LIDARs in neural network with steering, but when people are driving the cars, they are using only the eyes to measure, for example, the car they are which is passing by, or some obstacle they are trying to avoid. So maybe the future is to make some kind of computer vision that is detecting the distance and the obstacles, and detect some objects that are passing from the side.
Yes, that's a very good, very good question. I think that the parallel to humans is good. I sometimes use it, like how it happens in nature, right? But also, we didn't develop LIDARs because they are energy. You need to send out something, right? Just staying away from what a laser is, right? But bats are perfectly fine with navigating on radar. So it's a valid argument, but it's also not like one that destroys the case for LIDARs, especially if you have full lighting environment in the mind. In my opinion, the best solution is fusion, right? Because, okay, as humans, we have vision and we are very good for it, but we need light, right? We need to have this headlights when driving at the night. And sometimes visibility is poor, and drivers slow down, right? Maybe a perfect system with more sensors, no, doesn't need to slow down, right? So I think the fusion is best, right? When we're starting with LIDARs, it's you have to start with something. If you design like the target solution which you want to see in 10 years, you will find it, I guess. But it's a very valid point, right? A fusion of LIDAR data and vision data and maybe some other sources. It's the correct approach. In most of papers in AI are in vision because there were breakthroughs. So you want to produce as many papers as you can, and also it's a cheap sensor, right? So there are advantages, but there's also reasons outside of, let's say, the pure efficiency, pure technical considerations. This is a very good question. So,
another question, how large was the space of parameters in the genetic algorithm? Because you said you had 9 generations of nets, and that was enough to train a neural net?
Yes. Each population was 100,
yeah.
And the input was small. That's the key. Because, as I mentioned before, solving this kind of problem with where you have walls consistently, it's very simple. When you think about it, you need maybe 50 points of LIDAR data to actually make it. Like when you think how difficult it is to understand where the walls are, right? So, of course, when you have a smaller dimension of input data, you train much faster, right? You find the optimal representations faster. But I think we had a degree of 200.
I was asking actually about the hyperparameters because you said that a new neural network layer can evolve.
Mm-hmm.
So the number of layers is a sort of a hyperparameter.
Yeah, I'm not sure what was the number of layers in the successful generation. I'm not sure. The starting parameters, I also don't remember. If you are interested, I can send you an email because I have the whole configuration file. There's like mutation rate, all kinds of mutation rates for different kinds of mutations. So adding layers, the starting number of layers, and weights are randomized. So, okay, thanks. So the entire purpose of neuroevolution is that you don't need to design, right?
Yeah, I was asking about the parameters that determine the architecture.
Yes.
So it's the number of layers, the number of neurons per layer, and what more? What else is there?
Weights. That's it. And also the network was recurrent because it was about a sequence. You needed to drive, and there were some side ways, right? So it needed to learn understanding that no, this first is bad, right? The first right is not correct way to go. So of course this is by creating a back connection to the ultimate layer from the output. So that was the entire architecture. The rest was the important part was parameterization of the evolution itself. But I think it's way simpler. It simplifies the design because it's just less parameters.
Okay, thanks.
Mm-hmm.
Do you consider using a map to navigate in such problems that you need to, let's say, take second left, not?
Yes, of course. An input to it can be just Google Drive directions, like another input to a system that decides, right? Okay. Can be the only one. But it's just if you have a known route, you can make such solutions. It doesn't make sense not to use the assumption, right? If you want to solve the problem.
And
on these tools, can we implement any kind of neural network, and how much is the input size of the data?
So what kind of tools?
You told about the tools, like Carla or Air Simulating.
Yeah, I don't know that much about Carla, but I think you can learn in this next presentation.
Last presentation.
Not the next one, the one after. Yeah. I managed to build and run Carla and play with it very, very little. And I think it doesn't offer ready solutions. It offers a place to plug them and see how they behave. But I might be wrong. I have maybe new release offers that. I would be happy to learn. You are presenting.
Yes, yes.
Yeah, exactly.
I'll say a few words more about Carl.
Yeah, so of course this is interesting. So we can talk, right? Anyway.
Do you have any approach for this, like weather conditions?
Weather conditions, not yet. But it's a common, it's something you can find in Gazebo and in Unity. So, no, not yet. In the mine, it's very important. Of course, it's something about
outdoors.
The question for the, let's say, the mural effect. Say, underground mural effect. If you have LIDAR,
yeah.
And then you have mural, you have multiple.
Yeah, there is something we did notice this in the data because in this mine they have like various at one point on the road on the other side they had small reflective things. Of course, that messes up the LIDAR data, but. In this scenario, you have control of the environment. This is an important part. You can remove them if you don't like it. But they don't interfere with what you want. Like, this is a very, very minor thing. Basically, it's very easy to filter with even a very dense filter. So, not a problem at the cell. If they place like hall of mirrors there, we would be in trouble. Would human drivers?
Did you test your approach in the scenario that you enter the tunnel? Did you already test the scenario that you enter the tunnel in autonomous mode?
No. This project, we are in the phase of simulation.
Yeah, but only simulation.
Like in the mining problem, in the mining case, we are a bit further, so you could get confused. I got lost in my presentation.
But is it the problem? Entering the tunnel? Is it the problem?
No, I don't think so.
Okay.
Localization.
Just
localization, right?
Autonomous mode, because you have LIDARs, you have shiny.
Yeah, it's not a problem.
It's not a problem. Okay.
I mean, you need to solve localization.
Yeah.
Right? Not depending on whether you are in a tunnel or not. Just using some other things. And of course, this kind of deep learning approaches we've shown that works well with the walls are not that good outdoor. So you need, let's say, a different approach.
Isn't that off topic quality of the road? Because you have to sometimes compensate on steering wheel when you have some holes in the track or something like this. Is a topic or is manageable?
The quality in the harbor is good. In the mine there are some bumps, but nothing in this region. It's not that serious. And you always it's not like we call it behavior of the steering wheel. It's always a reaction to what you see. So even if we find a new way. So in the principle, the system works in a robust way in this aspect.
Last question. I have one about the second scenario, so the harbor. You've shown some detections and categorization of the cars on the road, and do you have do you have your own solution, or you are just getting the detections?
No, this is just visualization from the ECU system.
Okay.
We have plans to maybe improve it also with some secondary measures. But here is they have their own visualization system as well. This is harness, so we integrate it.
I was asking because there are a lot of methods that use 3D laser scanners to detect cars and identify.
These scanners are really simple and they're noisy. It's a good detection considering
just one comment on that here, because typically you get from the LIDAR, not solid state LIDAR, but the LIDARs that are implemented on the market, just a few points. So the detections are based on the rigid body principle and on the, let's say, time window approach to analyze the movement of the rigid body. And so it's sometimes very hard to detect if we have a pedestrian or a vehicle if you have just 10, 12 points from the detections. And if you are talking about solid state LiDARs, like the one that Energy or ND or others will implement, this is like high resolution LiDARs that almost look like an old fashioned video, so it's a low resolution video.
But we will work with these LiDARs. We are set on it, so that will make some problems cheaper.
Okay. I think we can continue this discussion with pizza and
Also, who's next?
Okay.
Just statements.